Okay, today our webinar will be about core log interpretation for formation evaluation. I would like to introduce myself. I am a senior petrophysicist in Ministry of Petroleum, Egypt, with 12 years experience related to formation evaluation of clastics and carbonate reservoirs, borehole image interpretation, rock typing, saturation height modeling, and integrated formation evaluation by using advanced tools like NMR geochemical tools. We will start our outlines with importance of core log integration, the scale and the vertical resolution for the tools, the difference between routine core and special core analysis, integration of logs and routine cores for formation evaluation, integration of logs and special core for formation evaluation. Why we say that we should use core log integration instead of using the petrophysical evaluation based on the triple combo only, which are the gamma ray, resistivity, and the density neutral. Why we should use the core integrated with the logs? The first reason, to reduce the high uncertainty associated with your petrophysical evaluation. For example, you are using Archie equation to calculate your water saturation. Are you sure that Archie is fit for your reservoir, or you need a calibration? So the core will provide you calibration for your water saturation. Also, when you're using porosity from neutron density or density alone, you need to check if your porosity is right. So you have to calibrate it with the core porosity. The second reason, to calibrate the different petrophysical parameters, like for example, the grain density, which are used as input in the equation of the porosity from the density tool. You needed to get it from the core data, not to use the default value of 2.65 for sandstone or 2.71 for limestone. Also, you need to use the A and M and N, which are the lithology exponent, the cementation exponent, and the saturation exponent from the electrical properties of the rock derived from the special core, and instead of using A equal 1 and M equal 2 and N equal 2. The third reason, it provides answers for reservoir characterization. The core log integration provides answers for reservoir characterization. We should know first what is the reservoir characterization. Reservoir characterization is to analyze the reservoir from micro scale to mega scale, starting with thin section, scanning electron microscope, up to mega scale like seismic reservoir characterization. So the core is essential for any reservoir characterization studies because it provides porosity, permeability, irreducible water saturation, reservoir quality by mercury injection data. So you can't use the logs alone for your reservoir characterization studies. The fourth reason is to construct rock types. What is rock types? Rock types is essential for any static reservoir modeling. Rock types are defined as rock with the similar petrophysical properties, porosity, and the same permeability. So any static model is constructed without rock typing. It's considered as a stochastic modeling. It's not respecting the reservoir property inside the reservoir. So you have to construct your rock types because rock types will be helpful for the modeler to interpolate between the values between the wells. So it's essential to use the core for rock typing construction because you can't derive the permeability without core data. The fifth reason is to build a saturation height model. The saturation height model is something, another model to construct a water saturation without using resistivity tool. This model is important for two reasons. The first, to quality control your water saturation, and the second reason is it is used as an input for any static model, especially in the transition zone. The sixth reason, when you acquire a core data, your sedimentologist will start to describe the fishes, and from these fishes you can colorate with your well log and start to make a coloration with the other wells. If you have more than one core data in the field, you can construct a lithofishes log, discrete lithofishes log, and make a machine learning algorithms to predict the lithofishes in the uncored wells. The seventh reason, I worked with borehole image interpretation for around 150 wells. The best method to start your borehole image analysis to start with the core well in the field and start to identify its lithophysis and calibrate it to the borehole image fishes, and then you can propagate to the other wells. The last reason, when you are doing a formation evaluation for the carbonates, you need to acquire a thin section to know the microfishes of your reservoir, because the microfishes always in the carbonate reflecting the reservoir quality. You can't say that mudstone is better than greenstone as a reservoir. It's always greenstone is better than mudstone. So you need to identify the microfishes based on the thin section and start to correlate these microfishes with your well log pattern. And if you have a large data sets of microfishes in your field, you can also make a machine learning to predict the microfishes in the carbonate in the other wells. The most important part about the core log integration, first, you have to make a depth matching between the core and the log. You will shift the core to the first run in the wireline logs because it is considered as the reference run. Moving next to the scale and the vertical resolution. The scale of the formation evaluation starts from microcentimeter, considered in the scanning electron microscope. The scanning electron microscope, you take the core block and put it in the microscope, famous as a scanning electron microscope, and it gives you details about the microcentimeter in the sample. When you are talking about the scanning electron microscope, it provides you information about your reservoir quality, your diagenesis. Moving up to higher scale, centimeter scale, which is the slabbed core. Also, you start to know if your reservoir as homogeneous carbonate or heterogeneous, or you check your fishes like it's cross-bedding, massive sand, hummocks. Moving up to a higher scale, which is the well log scale. So you need to upscale your information from scanning electron microscope up to well logging. The best part about the core, it has the ability to resolve the thin layers. What is the thin layers? The thin layers is the thin bits that are beyond the vertical resolution of the tool. So you will ask, what is the vertical resolution of the tool? The vertical resolution of the tool is the ability of the tool to differentiate the thin bit from the other thin bits. For example, you have 2 centimeter sandstone, and the vertical resolution of the tool induction is 3 or 4 feet. So it will be below the vertical resolution of the induction tool. So the induction tool will not read this sandstone. It will read an average value between the sand and the shale. So you need to identify these thin bits. So core provide you an answer to identify thin bits. There is a relation between the depth of investigation of the tool, the depth of investigation, how much the tool can read in the formation, with the vertical resolution, where the vertical resolution of the tool is inversely proportional to the depth of investigation. Induction tool has the highest depth of investigation, while the density tool has the lowest depth of investigation. The density tool has the highest vertical resolution, as we see here, and the induction tool has the lowest vertical resolution. Moving next to know what is the difference between the routine core analysis and the special core analysis. You acquire the core by using a core bit. The core bit is drilling. After you choose your core point, starting, then you will go out with your drill pipe and then go inside again. Using your core bit, you will extract the core you want, for example, 30 feet, 60 feet, 90 feet. The core bit is extracted from inside the well and go to a core barrel inside the drilling assembly and get back to the surface. After get back to the surface, it will be cut into small pieces by the engineer. The pieces, for example, are 3 feet long. Then these pieces are used for the well side as a description of the core, and then will send to the core yard. After it will send to the core yard, it will be cut by a core assembly into 2 halves. Half will be preserved for further studies in the future, and half you will do your analysis in this half. You can see that this example in the right, for example, this is a 3 feet long for one piece of the core. You have to do two things. First, you will go to the core yard and start to choose the core block. The core block is a small block or extracted from the core to do your experiments. These core blocks should be representative of your reservoir property. When you see in the example in the right, this is homogeneous, for example, this is homogeneous sandstone. So you will take the core block horizontally and vertically like this. But when you have a seam beds, it's preferable to take two core blocks in these 3 feet long. One in these fishes and the other in these fishes, and also you can take this other in these fishes to differentiate the variation in the petrophysical property from the core. There are 2 types of core. After acquiring the core, you will do some tests under these 2 types. The first type is called routine core analysis. The second type is called special core analysis. I have worked with around 200 core data in my project. All of the core acquired in the well are always has core porosity, core permeability, and core vertical permeability and the grain density. These data are essential with any routine core data. But the other studies in the routine and all the studies in the special core require extra fees to do these tests. So it's not acquired in all the core wells. It is acquired based on your request. The request of the petrophysicist, the request of reservoir engineer, and the request of the geologist. The 3 are in one team, have an agreement between each other to decide which tests will be beneficial for their field development plan. The basic tests for the routine core analysis are considered to be core porosity, core permeability, grain density. The extra test for the routine core are dense torque water saturation. Dense torque water saturation, we will talk about it later. It's very essential for calibrating your water saturation. Also, sedimentological studies like scene sections, XRD scanning, electron microscope, lithophysis, and the positional environment. These studies are essential for any geologist, but also they are essential for a petrophysicist. If he will start to make a rock types, he need a calibration based on the scene section and the scanning, and start to make a relationship between the rock types and the lithophysis. I have worked in several projects. I found there is sometimes a good agreement between the rock types and the positional environment and lithophysis, and sometimes not, which are related to diagenesis. That's why scanning electron microscope is very important. The special core analysis is more expensive than the conventional core, but it's very essential for any field development plan. It gives you a porosity permeability at overburden stress, because as everyone knows that the porosity and the permeability underground are affected by overburden stress. So you need to compare your porosity from the log under overburden stress with the total porosity you calculated. The electrical properties of the rock represented by E and M and N, as I mentioned, they are essentials, especially for the carbonate formation evaluation. Relative permeability curves, which are important for dynamic simulation and are important for constructing the petrophysical cutoffs, and irreducible water saturation. Wettability, it's important for your reservoir characterization to know if your reservoir is oil wet or water wet. Capillary pressure, which is important for saturation height modeling and reservoir quality evaluation. Also, mercury injection is important in reservoir quality evaluation and saturation height modeling. NMR, nuclear magnetic resonance tool, is very important for formation evaluation. So you need to acquire an NMR on core data to calibrate the NMR from your logs. And lastly, the geomechanical studies, which, for example, represented by uniaxial confining stresses test. Something important you need to know, when you are analyzing a carbonate with isolated vugs, you don't do a core blocks. You will make a whole core analysis. The whole core analysis will take the 3 feet core and will make the measurement of porosity and permeability in this whole core due to the presence of isolated pores. So if you, for example, take a core blocks in an isolated vuggy carbonate, you may take your core block in the matrix, not in the pores. So you didn't acquire the actual porosity and permeability of your reservoir. Now we will talk about your workflow for integration of logs and routine core for your formation evaluation. You start your workflow by quality control of your core data and the quality control of your logs. How you start your quality control for the core? You have your sedimentologist. He will describe your scene section and the scanning and lithophysis. and you start to compare the lithophysis and the scanning if you have any oesogenic minerals in any diagenetic effect cementation, and your core scene section if you have a quartz arenite clean sandstone with interconnected porosity, for example, and you have a good lithophysis and you have no cementation, and then you find the porosity permeability acquired from the tests are very low. That doesn't make any sense. So you need to get back to the core lab and ask them why the permeability, for example, is very low. Please take the test again and start to compare the test before your quality control and after your quality control. Also, if you are working with carbonate and found channel porosity is the fracture porosity from the scene section, and there are a lot of them in the scene section, and then you find your horizontal permeability is higher than vertical. That also doesn't make any sense because the fractures make the vertical permeability higher than the horizontal permeability. So you will go back to the core lab and ask them to make the test again. Regarding the logs, it's important to check if the gamma ray and the resistivity and the neutron density are aligned at the same depths. Also, you can compare the density neutron in a marker bed like anhydrite. It's not porous, so you will check the density value in this marker bed with the nearby wells. And if you have a difference between the wells and the offset wells, you need to do normalization for your logs, or you start to ask the acquisition company why the density is different in this well compared to the other. So if you done your quality control in a wrong way, all your formation evaluation will be wrong. So quality control is mandatory for any integration of logs and routine core for formation evaluation. Moving next to the first method in the integration of core and logs, the volume of clay calculation. The volume of clay are calculated by different methods, like volume of clay from gamma ray, volume of clay from neutron density, which is one of my preferred methods, especially in water-bearing reservoir or oil, and also volume of clay from NMR, also one of my preferred methods. NMR, someone is asking, NMR can be used in routine core analysis too? Yes, NMR is considered to be as a part of the special core because it required extra fees. NMR, you have to acquire the NMR data in the core in a water-bearing sand, for example, to derive the actual T2 value of the reservoir. T2 value, we will speak about it later when you are discussing the integration of logs and the special core for formation evaluation. So when you are acquiring any NMR logs in your reservoir, it's preferable to calibrate with the core. We will talk it about later. After you calculate the volume of clay from gamma ray and the neutron density, you need to check if your volume of calculation is right. You will take the core block sample and put it in an instrument called X-ray diffractogram, XRD, as a whole rock, not fractionated. This whole rock will measure by relation between 2 theta and d spacing, something extracted from the X-ray diffractogram. Every mineral have its fingerprint for the relation of the 2 theta and the d spacing. These spikes, as we can see, reflecting the volume of the minerals. By some equations, you will convert these peaks into volume of minerals. As we can see in the first row here, a quartz 75% from 100% total rock, potassium feldspars 4%, plagioclase 14, calcite cementation 0, dolomite, ferron dolomite 1%, pyrite, anhydrite, clay. Clay is 6% here. So convert this 6% from a dry clay into wet clay, because when you are using well log for volume of clay calculation, it's a wet clay, not dry clay. You will convert this dry clay by equation based on a grain density and the density of the sandstone or lime and the total porosity into wet clay. After you convert it into wet clay, you will calibrate your volume of shale from the logs with the volume of shale from XRD. In this example, we can see very good match, which indicate your calculation is right. Moving next to the third method for your integration of logs and routine core for formation evaluation are the grain density. You derive the grain density values from the conventional core by a method called helium grain volume method. So you will have the grain density of the rock. The grain density represents the density of the grains in your rock. The best method is to use this grain density in your equation of the porosity from the density tool. As we know, the porosity from density equal rho matrix, which is the grain density, minus rho bulk, which is the bulk density, divided by rho matrix minus rho fluid, which is the fluid density. But take care, you need to use the average grain density for each features. For example, your geologist divided your reservoir into 4 zones. One zone is fluviatile channel, the other zone is shore face deposits. You will use the average grain density for fluviatile and the average grain density for the shore face in your equation. What about the raw fluid? Raw fluid is derived also with the relation of the bulk density of the log with the core porosity. By this relation, we put the bulk density in the x-axis and the core porosity in the y-axis. And this is points for isofacious, for example, of fluviatile facies. You will draw a trend line and extrapolate this trend line to core porosity 1 or 100, based on your scale, if it's 0.15, 0.13, or 10, 20. The most important part to extrapolate your bulk density at porosity 100%. So this is representing the fluid density of your fishes. With the core data, the porosity from the density has the highest accuracy due to you derived the raw matrix by the grain density and you derived the raw fluid by this plot. Now you can trust the porosity from the density with using core data. Imagine if you don't have a core data, you can't derive the raw fluid and you can't derive the raw matrix. This is the most important part about the integration of logs and the routine core for formation evaluation. Moving next to helium porosity. Why we use helium in measuring the porosity? The helium is considered as inert gas. It doesn't react with the grains. It can move through small interconnected pores, but you should take care it move only through the interconnected pores. I have worked with around 100 or 150 wells with the core data. I made a lot of calibrations between the total porosity from the log with the core porosity. I always find in Egypt a good match between the total porosity and the core porosity. The reason for that, the method of preserving core samples. In the lab, they put it in the oven and expose it to a high heat, 100-degree temperature. That will evaporate your clay. The place where the clay evaporated become pores. So now you have to compare your core porosity with total porosity. As you can see, this is a paper I published 2021, a good agreement between the total porosity from the density with the core porosity. Moving next to Dense torque water saturation. What is dense torque? Dense torque is the best method to acquire water saturation in core only in one case, if you have an oil-based mud and your reservoir is at irreducible water zone. When you have that, you should do dense torque. Dense torque is very easy. It's based on putting a block in an instrument, and under this instrument you have your solvent. You start to evaporate your water. The evaporated water will go to the block and make the water in the sample also evaporated, and then will go to the right to the condenser. This condenser, it will condense the evaporated water into a volume of water, and you measure the volume of water. But you should take care the volume of water here is distilled water because the salts remained in the block. So you need to convert your distilled water into salt water by some equations, and then you have the volume of water, you will convert it very easy into water saturation. When you have the dense torque water saturation, you should use it for the calibration for your water saturation calculation from the logs. Either if you use Archie, use Simendo equation, Indonesian, even if you use SIMBED analysis, you need to calibrate your water saturation from the log with dense torque water saturation, but only in one case. If you have oil-based mud and you are irreducible zone. What is the irreducible water zone? The irreducible water zone that the water present in your reservoir is irreducible, can't get extracted with the production. And they include the clay-bound water, the water attached to the clay, and the capillary-bound water, which are the water present in micropores. Moving next to the most important test for any routine core data is the permeability. The permeability is essential for any static and dynamic simulation. You can't do your dynamic simulation without permeability. And the best method to have a permeability is your core. It's very easy based on Darcy law. You put the core block in a test and you measure the flow rate. You have the flow rate measured. You have the area of the core block. You have the difference in pressure in and pressure out. You have the length of the core block, and you have the viscosity of your nitrogen you use, for example. So the missing value will be only the K. By this equation, you will derive the permeability of the core data. After you derive the permeability of the core data, you need to calculate or predict the permeability in the logs. There are a lot of methods you can use to get this core permeability and put it in the log permeability. How? The first method is called Buckles plot. Buckles plot is a relation between water saturation and porosity, but it is used, this plot, only in the irreducible water zone. The intersection line we can see here is called K buckles, the permeability value based on the intersection of your water saturation with your porosity. But this is empirical method. It for sure it have a lot of uncertainty. I worked with it a lot. Some reservoirs it gave me a permeability have matching with core, and other reservoir didn't give me a good match. So this method is not reliable so much. Moving next to NMR permeability. The NMR log analysts and domain champions always market that the NMR provide you answers for formation evaluation. They provide you a porosity permeability. Yes, they provide you a permeability, but it needs calibration with the core permeability. You need to correct your permeability from NMR with core permeability. Unless your permeability from NMR is useless. The third, and for me is the best method, I have worked also for 6 years, how to predict the permeability in the wells based on the core permeability. You have a lot of methods. You can use a linear regression between the porosity and the permeability for each features. You can use multiple linear regression based on different well logs of the permeability with density, with gamma ray, with PEF, or you can use the machine learning algorithms like neural network. This is example a neural network from my paper published 2021, and the regression was 0.92. That was a good regression between the predicted permeability by neural and the permeability of the core. Also, you can use other machine learning, not neural only, random forest regression, gradient boosting, decision tree. So the challenge for any petrophysicist, how to predict the permeability in the logs based on the core permeability. Moving next to identifying the seam beds by using core. This example, you can see a seam beds. When you have a seam beds, your model will be different than using water saturation. You will make a model called seam bed analysis based on Thomas Steiber diagram, which is a relation between the volume of shale from gamma ray neutron density and your total porosity. And you will do some models and reconstruction of curves until you derive the porosity of the sand and the resistivity of the sand. Because, for example, this is a seam bed, the vertical resolution of the tool will not give you a detailed information about this sand. It will give you an average between the shale and the sand. So you need to remove the effect of this shale to derive the resistivity of the true sand. By using seam bed analysis model called the low resistivity model, you can derive the resistivity of the sand and the porosity of the sand. Also, seam sections is helpful to identifying your mineralogy. For example, if you have a siderite mineral, a siderite is called iron carbonate mineral. This iron carbonate increases the density value of your reservoir. So you can find the porosity from the density is little low because the density was high based on external mineral. So you need a correction of that. Seam section will help you to identify the minerals present in the reservoir and their effect on your well logging response. The last and the important part about the conventional core data with the logs is construction of log types. You will construct your log types based on several methodology like reservoir quality index relation with normalized porosity index, if the oil flow zone indicator histograms, Lorenz plots, Welland plot, all of these plots are used to construct a rock type in the cored well. The challenge how to construct the rock types in the uncored wells. You will use also a machine learning classification algorithms. After you construct the rock types from the core, you will predict the rock types in the uncored wells by several machine learning algorithms, also neural network, decision tree, random forest. This example of the paper published 2021 showing that this discrete rock type in the core, and this is the continuous, discrete log type predicted based on logs. We can see a very good match in the rock types, except at one, but the accuracy of this model was 90%. So after you construct your rock typing, you can use machine learning algorithms to predict the rock types in all the uncored wells. The last part about our presentation, it will be the integration of logs and the special core, not conventional core, the special core for your formation evaluation. Someone is asking what is the best method to determine porosity and permeability in carbonate. It depends if your carbonate is intercrystalline carbonate or interparticle for limestone, intercrystalline for dolomite. You take a core plugs and make also nitrogen method for the permeability and helium methods for the porosity. But if your carbonate has an isolated flux, you need to do a whole core analysis. You will take the core as a whole and make the measurement of porosity and permeability in the whole core. But how you know that you have an isolated flux? Something called the CT scan. You will take the blocks and put it in a CT scan, and it show you CT scan if your porosity is uniformly distributed or is it heterogeneity. Another question, is there limits in dense torque analysis for core block? Yes, there is a limitation. If you have a water-based mud, you can't use a dense torque. If you are in the transition zone, you can't use dense torque. But I worked with around 8 wells with a dense torque water saturation. All of them was on oil-based mud at is the irreducible water zone. So they gave me a good calibration. Speaking about the last part in the special, in the integration of logs and the special core for formation evaluation, one of the best part for any petrophysical evaluation to use the electrical properties of the rock from the special core data, especially in the carbonates. What is the electrical properties of the rock? The electrical properties of the rock represented by A and M and N. A is called the lithology exponent. It's based on your lithology. M is called the cementation exponent. It's based in your reservoir. If it's connected porosity, it's isolated pores, because the M depending on the passing of the electrical current through the block. If the pores are interconnected, the passing of the electric current is fast, so the M will be low. But if the pores are not connected and isolating, it will take time to pass your electrical current, so the M will be high. The N is called saturation exponent, and it depends on notability. How we derive these tests in the core? We measure the core block. We saturate the core block with 100% water saturation and measure the resistivity. The resistivity is called R node. It's called the resistivity of the core block with 100% water saturation. And then we measure the resistivity of the water alone, and it's called RW. So you have something called the formation resistivity factor, a relation between R node and RW. And in the x-axis, you put the porosity. You draw trend line. The slope of the trend line equal M. The intercept equal E. So now you have an E and M. How you derive the N? By something called the resistivity index. The resistivity index, after you saturate the block with 100% water saturation, you start to desaturate the water and saturate oil. After you saturate the oil, the RI is called the resistivity the resistivity of the rock over the resistivity of the water, R node. So the resistivity index equal Ri over R node. And in x-axis water saturation, the slope here will be N, which is the saturation exponent. So by special core data, you will have A and M and N measured, not default value as mentioned in textbook. You will use A and M and N in Archie. So you will decrease the uncertainty associated with water saturation calculation from Archie. Moving next to the relative permeability curves, they are very important for any reservoir engineer and also for me as a petrophysicist. I use them to know the wettability of the reservoir. I use them to construct my petrophysical cutoffs based on endpoint of the relative permeability of the oil. I take the endpoint of the relative permeability of the oil for each block, and I have the absolute permeability. I make a plot between both of them and know the cutoff permeability value for my reservoir. So I can use this cutoff permeability value for my reservoir to construct the net reservoir cutoffs. Also, the relative permeability curves can provide me with irreducible water saturation, like Dennis-Stork. But here, the best part about it, it doesn't affected by if you have a water-based mud or oil-based mud. So you can use the irreducible water saturation from relative permeability to calibrate your water saturation from log, but only in the irreducible zone alone. But there is another way. After you calibrate your water saturation from the relative permeability curve with your log and you find a good match in the irreducible zone, your equation is working in a proper way. Moving next to the capillary pressure data. The capillary pressure is based on injecting the sample. The sample are saturated with water. I pour split method. I saturate the sample with 100% water, and I started to inject gas. The injection of gas started to displace the oil, the water. Sorry, the extracted water are measured as a volume of water saturation. But when I am injecting the gas, I am injecting it with a capillary pressure called PC. So I make a relationship between capillary pressure and water saturation. For every reservoir, they will be different. Based on capillary pressure and water saturation, I use them in some mathematical models, for example, like J function, to start to construct an empirical relation between the water saturation and G. So I can obtain my water saturation of reservoir based on a function like J function or like Tomer function or like Brooks and Corey. These methods are working very good to calibrate your water saturation, but there's something you should put in your mind. You need to construct your saturation height model built in a right way. You need to predict the porosity and the permeability because they are used in the saturation height model build. So after you construct your saturation height model, you will apply it to the log. How you will apply it? For example, you made an empirical equation between SW and J. You have the J function, J value, you will drive it based on the height above the free water level. You have the porosity and the permeability. Then you will drive something constants called A and B. They are based on a power function between water saturation and J instead of capillary pressure. So you can drive your water saturation based on A and B constants you obtained from porosity permeability, and you have the J based on height above the free water level. Now you have a water saturation from your logs without using resistivity tool. And start to compare, as we can see in this example, water saturation from the Dennis-Stork with water saturation from saturation height and with water saturation from Archie. The three are in a good match, which indicates the model is right. Moving to the last two parts inside the integration of logs and special core for formation evaluation. The mercury injection data. The mercury injection data are mandatory for any reservoir quality evaluation. If you want to know the reservoir quality, you need to acquire mercury injection. The mercury injection is a simple test. You just desaturate your plug from any fluid, and the plug becomes desaturated, and then you inject mercury. The mercury will be injected. The volume of mercury will be inversely proportional to volume of water saturation. Some empirical models are done and mentioned that when a pore throat is filled with 35% mercury saturation, these pore throats represent the reservoir quality, and it's called R35. So Welland in 1992 made an empirical relation, but only in intergranular and interparticle sandstone and limestones, to obtain R35 based on porosity and permeability and he made this empirical equation. I worked with this empirical equation in many fields, and I always find a good agreement between R35 from the logs with R35 from the mercury injection, but only in the interparticle and intergranular porosity. I didn't find any match in the heterogeneous carbonate like isolated vox. So mercury injection is used for reservoir quality evaluation, and also it can be used for saturation height. The mercury injection provide you with capillary pressure and water saturation. But my preferable method is porous plate because it has less corrections. Like porous plate need only reservoir to fluid lab conversion, while mercury injection need 2 extra corrections, clay bound correction and closure correction. Moving last to NMR, you have to derive the T2 cutoff. The T2 is called the relaxation time of your reservoir. Any peak below a T2 is called capillary bound water or clay bound water. So summation of a clay bound water and the capillary bound water is called irreducible water saturation. Based on this method, the irreducible water saturation and the free fluid is any peak above a T2 cutoff. Based on empirical relation, we can derive a permeability. So you need to make acquisition of NMR on your core block and derive a T2 cutoff for each core block. To apply these T2 cutoffs for the NMR logs to derive the actual T2 and derive the actual irreducible water saturation and actual permeability. Sometimes you find a lot of wells I worked with NMR on logs without core. It's challenging because the T2 cutoff, the surface company always tell you use 33, but this is not right. Something like glyconitic sandstone will change your T2 cutoff. Something like fine sand will change your T2 cutoff. So you have to acquire NMR on your core blocks and construct the T2 continuous curve for each core block and calibrate them with your logs. When you do that, you will have a precise irreducible water saturation from NMR and the precise T2 distribution and the precise permeability data. Now we have finished our presentation, and now it's time for any questions.